All right, you guys, this is the video that goes through the 3 examples that we didn't get to in class. For these notes, I'll always go back, and if we modify problems that we do in class, in order for you to get notes that correctly match up to the slides from your classmates, I will change the information on the slide. So for instance, with this slide, it indicates that we completed a problem where we changed the bounds of that piecewise function so that we were working with 0 instead of 2. So just know that that will be available for you. I'm working with Google Slides for this presentation, and typically the videos that I do are with PowerPoint. So some of the going between slides might be a little bit clunky here, but just bear with me for that. So the next type of limit that we wanted to talk about today is a limit that comes from a step function. And a step function is just going to result in steps graphically. And so like piecewise functions, there are going to be discontinuities or jumps. And specifically with the work that we have here with this absolute value function that is divided by x, we have a step function that occurs at 0. So if we were to graph out this function, what we'll see, I can draw my x and y axes here, is that as we come close to 0, the value will approach 0 and then have a discontinuity here. So up until 0, we will be at -5. Then right away when we hit 0, it will jump up to 5. Again, not defined at 0, but that is where the jump occurs up to +5. You can check this function here in your graphing calculator. And again, just make sure you're using the absolute value function there. Whatever this constant is, that 5 there, is going to change the value of the steps. So for instance, if we just had a 2 there, it would go from -2 up to +2. So what we want to consider is, how does that affect our limit evaluation? So this function, we can talk about the limit as x approaches 0 from the left-hand side of our function. That value is going to be what the y value is up until we actually get to 0. So in this case, that's going to be -5. We can also talk about the limit as x approaches 0 from the right-hand side. So that's if we're coming along this way, right to left. That value for our function, as we get close and close and close to 0, is going to be +5. Because these two values are not the same quantity, that means that our limit, if we are only asking as x approaches 0, is not going to exist. So we'll simply say DNE. Now this type of behavior is something that you're going to see with any step function. So an absolute value divided by our linear term here, that's one example of a step function. You'll see lots of step functions where you have the category that applies up to a given level, then you jump up to another category. So things like salary levels or income levels, tax brackets, those are going to be applied examples where you are at one level until another year causes you to jump up. So you're just moving in increments that look kind of like stairs. Greatest integer functions, ceiling functions, floor functions, all of those are examples where we'll see those jumps, and you'll have well-defined left and right-hand limits, but they will be different from both sides, so you won't have a single limit. So the next section of limits that we want to discuss are going to be unbounded limits. And really you just want to think of these as limits where you have asymptotes that cause you to go to positive or negative infinity. So one thing to note is that we do refer to limits that tend towards infinity as an example of limits that don't exist. Unless a limit does not have a defined value, it's not going to technically exist. But as it notes here, we're going to have to be more specific as we move forward. So we will need to identify whether trends are towards positive or negative infinity and what that looks like from the left and right-hand side. So do know that we will come back to talking about asymptotes frequently, but right now we just want to touch on the fact that unbounded limits are another category of limits that don't exist. So let's see what the graph is that we're dealing with here. And I'll try to pull that pen back up. So in this category, we're looking at the limit as x approaches 1 of 4 divided by x minus 1 to the 4th. So again, this is one that we can plug into our calculators. But what we find is that as we are approaching 1 from either side, 1 going into this expression would cause us to divide by 0. Anytime we have division by 0, we have trend towards infinity because of that asymptotic behavior. So here, our particular graph is going to head up towards infinity on this side, and the same from the right as well. So looking at this expression, and my 1 is a little bit off-centered, it should be more right here in between those values. So as I come to 1 from the left-hand side, my behavior is tending towards positive infinity. As I come from the right-hand side, it's also tending towards positive infinity. And you should check this graph in your calculator. However, what that means is if we are asked to identify the limit as x approaches 1 of our given function, at this point in time, we can simply say it does not exist. However, like I mentioned before, we are going to be more specific in the future. We're going to look at the left and right-hand side, and specifically whether or not it goes to positive or to negative infinity. All right, we've got one more category of behavior that we want to talk about for where limits don't exist. And this one is in many ways the most unique of the different trends that we look at. And this deals with oscillatory behavior. So this is when you have graphical behavior that moves back and forth in a continuing motion and never rests in one position or never can be tracked down to one position at a given location. So in general, when you think about things that are oscillating, just think about back and forth motion from a very fundamental level. So you're going to need to understand how oscillations occur if you do any future study in physics, chemistry, and engineering. And this slide just contains some examples. So physicists love oscillatory behavior. They talk about it frequently with harmonic motion. The way that atoms interact will also depend on oscillations. In chemistry, there's a category of reactions that are oscillating, which means that they never will reach an equilibrium point. For mechanical engineering, there are certain things for what you would put into a rocket for combustion-driven oscillators, so things that are working to power your systems, more or less. So lots of examples in the real world where you're going to observe oscillations. So just like any other function that we encounter, we want to be able to describe what's going on when things are oscillating. And one of those abilities to perform descriptions is going to involve limits. So let's check out an example of a function that oscillates as it approaches a given value. So you are going to want to plug this function into your graphing calculator. So that way, if you haven't seen something that's oscillating before graphically, you get a chance to see what that looks like. So I'm going to sketch this out. And what we'll find is that this function comes in and then it oscillates rapidly back and forth here. And this is going to be true for sines and cosines, the work that we do with trig functions. Now this function is going to go back and forth from different values. And the reason that it's going back and forth, back and forth, back and forth is because cosine itself is a periodic function. So it's going up to 1, down to -1, up to 1, down to -1. So as we plug in subsequently smaller and smaller values, we're getting those outputs from trig functions which move in a periodic motion. And in this case, again, we can't plug in 0 directly because we can't try to divide by 0. So this function is not one that we can pin down to a specific value at 0. So on your graph, go ahead and try to zoom in as much as you possibly can. And the more that you zoom in, the more that you see the oscillatory behavior back and forth like this. So this is another example of a limit that does not exist because it's never going to hit a point that we can track down in space at 0. So those are the 3 different limits that we want to make sure we are aware of. There is an AP practice problem here. So I'd like you to take a look at this just to see the first type of way problems might be posed to you on the AP exam. So this tells us the figure above shows the graph of a function f with a domain between 0 and 4. So we need to figure out which of the statements is true. So let me pull up the pen again, and let's analyze each of these statements. The first one says, the limit as we approach f of x from the left-hand side the limit as x approaches 2 from the left-hand side of f of x exists. So that means we're coming towards 2 from this side. So my function appears to be getting closer and closer to, this looks like about 2 up here on the y value. So I do have a left-hand side limit. I'm good to go there. Then it's telling me the limit as x approaches 2 from the right-hand side, so the positive side of f of x exists. So if I come in from the right-hand side, this function here appears to be approaching 1 from the right, so we've got a limit. Last statement, the limit as x approaches 2 exists. Well, it doesn't, because this value here is different from this value here. If your limit is not the same from both sides, then the overall limit doesn't exist. So only 1 and 2 are going to be true. So in this case, our answer is going to be C. And that's one of the cases of how limit work could appear on the AP exam. Last thing for today, if my slide will change. I'm swiping at it right now, but it's not changing. Okay, well, the last slide is just about your homework. So if you took honors pre-calculus last year, it's possible that you would have been assigned many of the problems from the textbook that you'll see tonight, previously during last semester. And that's okay. It's fine to practice similar problems again if you haven't seen them in a while. And we will also have those Khan Academy practice problems that give you some more information about graphing. So make sure you get through those problems. Check Calc Chat if you need any assistance, or come and see me after school. And then also don't forget to screenshot the Khan Academy and include a summary in your homework. So that's it for this video. Hopefully that didn't take too long to get through, and that's clear overall. Tomorrow we'll dive into how you can calculate limits analytically, which means we don't rely on a graph or on a table.